Hello students. In this video lecture, I'm going to open the door to Chapter 21 of your textbook. Chapter 21 deals with carboxylic acids and their derivatives. In this introduction to the topic, I'm going to discuss the nomenclature of carboxylic acids. I'll take a look at some of their important physical properties, and I'll show you a couple of new reactions that can be used to synthesize carboxylic acids. Okay, first, nomenclature. Some of the smaller molecular weight carboxylic acids have common names. Let me focus now on the IUPAC rules for naming carboxylic acids. I'm going to take this compound as an example. One finds the longest unbranched chain of carbons. You count the number of carbons. That's 1, 2, 3, 4, 5, 6. All right, for a starting name, you write the name of the corresponding unbranched alkane with the same number of carbons, and that would be hexane. The next step is to drop the E and add a special suffix, namely oic acid. And so it becomes hexanoic acid, and that's the official IUPAC name for this carboxylic acid. The main functional group of a carboxylic acid, we call it a carboxyl group. Carboxyl group. All right. If you have substituents present on the parent chain, how do you name it? Well, let's take this as an example. Find and count the number of carbons in the longest unbranched chain. That's 1, 2, 3, 4, 5. The starting name would be pentane. All right, we drop the E and add oic acid. That gives us pentanoic acid. Now on this parent pentanoic acid chain, we have two substituents. We have a methyl substituent attached here, and we have a chlorine or chloro substituents attached here. And then we're going to number the carbons. Carbon number 1 is the carboxyl carbon. Then number the carbons going down the chain. We've got 1, 2, 3, 4, 5. Right. We're going to now name each substituent and indicate with it its location number. So, and then they're named alphabetically. So alphabetically, chlorine or chloro comes first. It's attached to carbon 3, so we say 3-chloro, and then 2-methyl pentanoic acid. This is all one word. There's no breaks or hyphens, except for the word acid. Of course, that's a second word. If you have a carboxyl group attached to a alkane ring, a cycloalkane, you name it in the following way. Let's use this example. This is a 5-carbon ring. You would say cyclopentane, and then a second word, carboxylic acid. So the name of this is cyclopentane carboxylic acid. All right, let's consider a case of where you have a compound that has two functional groups, one of which is a carboxyl group. In the example here, we have a 4-carbon compound has a alkene group and a carboxyl group. The question is, should we name that as a carboxylic acid that contains an alkene group, or should we name it as an alkene with a carboxyl substituent? In IUPAC, the rules work like this. If you have two functional groups, they're going to have follow a nomenclature priority rule. The group that has more oxygens was given a higher nomenclature priority. In this case, our carboxyl group has 2 oxygens. The alkene has none, so this will be named as a carboxylic acid containing a CC double bond. All right, in this particular case, we count the total number of carbons. It's 4. We're going to say butene. We don't want to say butane because there is a double bond. Butene and then with the usual suffix buteneoic acid. All we have to do now is indicate where the double bond is located. We do that by numbering the carbons of the chain. Carbon 1 is a carboxyl, then we go 2, 3, 4. The double bond is between carbons 3 and 4. Remember the rules in naming an alkene. Use the lower of the two number, that's 3. Put the 3 in front, followed by hyphen. So the IUPAC name of this is 3-butenoic acid. All right. You could have a so-called aromatic carboxylic acid. That's where you have a carboxyl group directly attached to a benzene ring. Now, we actually saw this in chapter 18. This particular compound, you don't name it as a carboxylbenzene. You give it a spatial unit name, which happens to be benzoic acid. So the IUPAC name for this compound is benzoic acid. If you had substituents, then of course, well, you know how to name those kinds of compounds. You saw that in chapter 18. And another important subfamily of carboxylic acids are so-called dicarboxylic acids, where you have two carboxyl groups at opposite ends of a carbon chain. In this example, well, the way you name it, count all the carbons. That's 1, 2, 3, 4, 5, 6, 7. The starting name is heptane. And then, because there are two carboxyls, you say di, and because the usual ending for carboxylic acid is oic acid, the name of this compound is heptane dioic acid. Now, all this so far is the rules according to IUPAC, but there are ways to name carboxylic acids by a so-called common naming system. In many instances, the common names are used more frequently than the IUPAC name. Now, let's look at some examples here. The smallest and the simplest carboxylic acid you could have is this, just one carboxyl group and a hydrogen. The common name for that is formic acid. The basis of the name is this, is that it's based on the Latin name for red ant. And the reason is that the venom of red ant is formic acid. This is, the common name is acetic acid. Acetic acid is the component of vinegar. Vinegar is a 5% solution of acetic acid. The Latin word for vinegar, I don't recall the exact Latin word, but acetic is based on that Latin word for vinegar. This 3-carbon carboxylic acid has a common name, propionic acid. It's based on the Latin name for fat, which is interesting because there is another important subfamily of carboxylic acids called fatty acids, which are long-chain carboxylic acids from 4 or more carbons, I think 4 to 28. They all have an even number of carbons. But basically, a long chain, 4 or more, thus the term fat, and yet we have a 3-carbon one where we're basing the name on the Latin term for fat. I'm not sure why that is. Here's a 4-carbon carboxylic acid. The common name is butyric acid. And this one's really interesting. If you've ever smelled butyric acid, well, it's notable about it is its unpleasant smell. I recall an older general chemistry textbook. I no longer have it, but in describing butyric acid, it said had the odor of dirty socks. Indeed, a way to describe the odor of butyric acid, let's say if you were to go to the gym, you do a vigorous workout, you take your clothes, your sweaty clothes, you put them in a bag, you don't wash them, you go back and put them back on and work out again and then put them back in the same bag, and you leave the bag for a week, and you come back and smell it. That what you're smelling there is, in fact, butyric acid. If there's a bacteria working on perspiration that produces the butyric acid as a metabolic byproduct. And it goes further. The one with 5 carbons is called valeric acid. I just don't have that written out. All right. Now, sorry about the smaller printing here. I want to look at compounds that are actually ionic compounds, where one of the anions is the conjugate base of a carboxylic acid. They're called carboxylate salts. Carboxylate salt. Here's an example of a 4-carbon carboxylate salt. I want to go into how those are named. And there's a basis. Well, fundamentally, the basis is IUPAC, but there is a variant of it that actually uses the common name. I'll try to explain. A carboxylate salt is an ionic compound. The general rule in chemistry for naming ionic compounds is that it has two names. The first name is the name of the cation, or a name corresponding to the cation, and then the anion name. And a common example would be the ionic compound sodium chloride, whose formula is NaCl. You can see the basis of the name. You name the cation first. In naming a metal cation, you just use the element name. And then you name the anion. There's a rule here. The single atom ions have an IDE ending, and so it comes from the element chlorine. Chlorine then becomes, as an anion, becomes chloride. So it's sodium chloride is the IUPAC name for this for table salt. All right, now let's look at this example here and how you name that. And there's two ways you can do that. One uses the IUPAC name for the corresponding acid, and the other the common name. Let's look at the IUPAC way of naming it first. The idea is that you want to establish a name for the carboxylate anion. That's the conjugate base of a carboxylic acid. The starting point is the name of the parent carboxylic acid. The IUPAC name for this 4-carbon acid is butanoic acid, 4 carbons. You change it so that it becomes the name of the carboxylate, and here's the way you change it. Drop the IC ending and the word acid, and then you add the suffix ATE, 8. 8 is a common suffix for anions that contain oxygen, like sulfate, carbonate, phosphate, and so forth. So the name of the carboxylate anion is butanoate. We've got the two names, the name of the cation, that's sodium, and then the name of the carboxylate anion, sodium butanoate, is an acceptable name for that carboxylate salt. Alternatively, you can name it using the common name for the corresponding carboxylic acid, and so let's see what this becomes when you apply that common naming rule. Well, the 4-carbon carboxylic acid, we saw that before, that's butyric acid. So to establish the name of the carboxylate, you start with the name of the neutral carboxylic acid, the common name, butyric acid. All right, you make some changes. You drop the word acid, drop the IC ending, and add ATE, just as we really did before, and that changes to butyrate. And so butyrate is the alternative way to name this 4-carbon carboxylate anion. And so the optional name you can use here for this carboxylate salt would be sodium butyrate. Sodium butyrate. All right, let's talk about some important physical properties of carboxylic acids. This is something we have done before in our discussion of alcohols, alkenes, and the like. There are some important trends with respect to boiling point for carboxylic acids. Now, to determine the relative boiling point of compounds, it is this. It's all about the strength of the attractive forces between the neighboring molecules in the liquid form. The stronger the attraction between the neighboring molecules, the more heat energy you have to pump in to drive them apart and convert them to liberated free vapor molecules. And so we find a simple relationship is that the stronger the attractive forces between liquid molecules, the higher the boiling point. All right, now let's take a look at acetic acid. It's also the IUPAC name would be ethanoic acid. And what's going on in a liquid form of acetic acid. Well, there are natural attractions between the carboxyl groups, and it's shown right here. You actually will have a double hydrogen bond. The acid on the right, the hydroxyl group, will be hydrogen bond attracted to the carbonyl oxygen of the molecule on the left. The molecule on the left's hydroxyl group will be hydrogen bonded to the carbonyl oxygen of the molecule on the right. So you have really a double hydrogen bond here. Now let's say compare that with two alcohol molecules. There's just on average a single hydrogen bond between the two. Two hydrogen bonds between adjacent molecules is stronger than one hydrogen bond attraction. Therefore, the attractive force in carboxylic acid liquid molecules is going to be greater, and you expect the boiling point of a carboxylic acid to be higher than, let's say, the corresponding alcohol. Indeed, the 3-carbon alcohol propanol has a boiling point of 97 degrees, whereas acetic acid has the higher boiling point of 118 degrees. All right, solubility in water. Now, this is something that we looked at in our discussion of aldehydes and ketones. It actually is applicable back to alcohols, but when we did the chapter on alcohols, I just skipped over that aspect. But the principles here apply across the board to all organic compounds. And if you recall, in the previous chapter, we worked out what's called a solubility ratio rule. And you apply a little formula. Based on the calculation of the formula, you can make a prediction whether a compound is water soluble or not water soluble, that is water insoluble. And here's the idea. You count the total number of carbons, right, and divide that by the number of hydrogen bonding groups. Now, since our focus here is carboxylic acids in the carboxyl group, I need to explain. I have condensed formulas for the carboxyl groups, but of course there is a C double bond O and an OH. We made the point, that it has two sites of hydrogen bonding. It might seem to be more strongly attracted to water than less. But things get complicated, and there are a number of offsetting factors, and it turns out empirically that even though the carbonyl group the carboxyl group got carbonyl and OH, it behaves like a single hydrogen bonding group. That's the way it works. It counted as just one hydrogen bonding group. So in doing this, the solubility ratio rule for this compound, the total number of carbons is 6 and 1 or 7. Divide that by 1, and then you compare that to 5. If it's equal to or less than 5, you predict it to be water soluble. If it's greater than 5, you predict it to be water insoluble. 7 is greater than 5, so we'd say this compound is water insoluble. And you can definitely attest that this is insoluble. I actually remember an experiment where we synthesized it, and not for our lab this year, but goes back a ways, and it's definitely insoluble in water. Let's do the second compound here. This 3-carbon carboxylic acid. The total number of carbons is 1, 2, 3. Carboxyl group again counts as one hydrogen bonding group, so 3 over 1, 3 less than 5. Indeed, water soluble. This compound, there is 1, 2, 3, 4, 5, 6 carbons altogether. Now there's 2 carboxyl groups. You count 2 hydrogen bonding groups. That's 6 divided by 2 is 3. 3 less than 5. So we're going to predict this to be water soluble. The idea is when the relative number of carbons is large, then it's going to be more hydrocarbon-like in its behavior. It's going to be more strongly adhering to the neighboring organic compounds. Water, even if it's pulling with a hydrogen bonding force, may not be able to pull them apart. But if something has a relatively large number of hydrogen bonding groups, then there is it really amps up in the number of attractions, strong hydrogen bonding attractions to water solvent. That tends to enable water to pull apart the solid molecules, causing them to dissolve in the water. And so that's kind of the idea here. Oh yeah, before we go on, in naming this carboxylate salt, the issue might come up is what's the water solubility of a carboxylate salt. And this is important. Not just a carboxylate salt, but any organic salt. The idea is that you do not apply the solubility ratio rule at all. And the reason is that regardless of the number of carbons, an organic salt tends to be water soluble. I mean, it's full ionic. There's a stronger attraction, electrostatic attraction to water molecules. And so, in general, organic salts, we predict them to be water soluble. In spite of the number of carbons they have. And so when you see an organic salt, do not apply the solubility ratio rule. Just simply go with the fact that it's ionic and an organic salt and predict it to be soluble in water, and generally you will be correct. All right. Now in this slide, gosh, I don't have a title to this, but what we're going to look at here is the synthesis of carboxylic acids, and then I'm going to show you 2 new ways to make a carboxylic acid. I don't have it written out on my PowerPoint slide here, but let's think about how one can make a carboxylic acid. You've actually studied reactions that will do that. I could give you a moment to reflect on that and ask, can you think of previously studied reactions that will enable you to synthesize a carboxylic acid? Well, we don't want to tarry too long here, but well, there's a number of ways, but one that comes to mind is in the chapter on alcohols, and also recently aldehydes. An oxidation of a primary alcohol using a strong oxidizing agent produces a carboxylic acid. The oxidation of an aldehyde also produces that, and that was, I hope that's more fresher in the mind. Aldehydes are so sensitive and easily oxidized, you can use the mild oxidizing agents, the WIMPs, the Benedicts and Tollens type reagents to oxidize them to carboxylic acids. Another way that comes to mind is in the chapter 19. If you have an arene, a carbon with an alkyl side chain, and you vigorously oxidize that, the alkyl side chain oxidatively degrades to a carboxyl group. If there's more than one carbon, you'll see carbon dioxide as a byproduct. But that's another way to synthesize a carboxylic acid. Well, all right. But what's the new ways? As I said, I'm basically going to show you 2. One makes use of a Grignard reagent. You make the Grignard reagent. Those in the lab we did have time to make the Grignard reagent. We didn't have time to finish out its reaction. But if you mix carbon dioxide and the Grignard reagent, and there's a number of ways to do that, well, interesting thing happens, and this falls within our pattern way of thinking about reactions. The Grignard is an organometallic with right anionic form. There's the anion in the cation form. The anion is going to act as a nucleophile. The carbon dioxide, interestingly, has two carbonyl groups. When you see a carbonyl group and you have a agent that can be an adding reagent, an addition reagent, well, addition will ensue. Indeed, you're going to get addition of the ionic ions from the Grignard reagent to one of the carbonyl groups. The G minus here, G stands for organic group, is going to nucleophilically be attracted to and bond to this carbon. And then let's say this oxygen bonding to that will be electrophile. So this, when those two attach, this C double bond O drops to a single bond. The other double bond stays intact. And you basically have, that's the addition product. This would be called it's a magnesium carboxylate salt. Magnesium carboxylate salt. It would stay there in your flask, and you could actually isolate it if you wanted to, but nobody does. What we do in a case like this is that we do an acid workup. We add aqueous acid. The acid protonates the negative oxygen. That converts your carboxylate to the carboxylic acid, all right? To the carboxylic acid, and so that will, this reaction is a way to synthesize the carboxylic acid. Grignard reagent and carbon dioxide. There are two ways to mix the carbon dioxide with the Grignard reagent. One is to take an actual tank and you bubble the carbon dioxide through the pre-prepared Grignard reagent in the ether solution. Now, the second way is really very cool, and in fact, it's often done as an experiment in undergraduate organic labs. A handy form of carbon dioxide is dry ice. Dry ice is frozen carbon dioxide. So what you do is you take a powdered dry ice and you physically pour your Grignard reagent solution into the powdered dry ice. Now, of course, you're going to do it in a more controlled way. You'd have this in a beaker and you draw up the Grignard reagent with a plastic pipette and you squirt it in. It smokes vigorously. And when the smoke clears, you've got this magnesium carboxylate salt. The second way to make a carboxylic acid, this makes use of a compound that we haven't done a lot of study of. They're called nitrils. Nitrils, also an organocyanide group, C triple bond N. We may have seen those as a substituent, let's say, in the Diels-Alder reaction, or substituent on a benzene ring. But the reaction here is the hydrolysis of nitrils. Hydrolysis means reaction with water. If we take the nitrile and water in excess, add acid, a fairly concentrated acid or fairly concentrated base, and heat, and you have to heat vigorously, probably an hour longer, you will get as your product this carboxylic acid, this hydrolysis product. Now you can see there's a whole lot going on. There are a whole bunch of addition, substitution, elimination reactions here. The nitrogen, you say, what happens to that? Well, depending whether it's acid or base, if it's under acidic medium, it will form an ammonium ion. If it's basic, it'll come off as the gaseous ammonia. It just diffuses away. But the reaction goes in good yield, and it's one of the standard important ways to synthesize a carboxylic acid if you have the starting nitrile. Hello everyone. In this video lecture, I'm going to begin talking about the reactions of carboxylic acids, as well as a subfamily of carboxylic acids. They're called derivatives of carboxylic acids. These include things such as esters or amides. And so this would be part 2 of chapter 21. We're going to focus on these 5 main reactions. 1, 2, 3, 4, 5. First of all, that carboxylic acids are weak acids. Secondly, there is a substitution reaction in which the hydroxyl part of the carboxyl group is replaced by another group, specifically by a nucleophile. This is going to be a very important reaction and that will include not only the carboxylic acid, but these carboxylic acid derivatives I mentioned, amides and esters. Number 3, we're going to look at the reduction of carboxylic acids and their derivatives. And then 4 and 5, number 4, reaction called decarboxylation, where the carboxylic acid is subjected to heating, which is going to cause a elimination of carbon dioxide from the carboxyl group. And then number 5, this is a halogenation of carboxylic acids. All right, number 1 first. As the name implies, carboxylic acids are indeed chemically acids. They are weak acids. Now, of course, a weak acid is an acid that if you put it in water, it's not going to dissociate completely, but only incompletely. It will dissociate to a point of equilibrium and then there'll be no further reaction. This equation illustrates that. G just stands for organic group. But if you place the carboxylic acid in water, it dissolves. It will dissociate, breaking off a hydrogen ion and leaving the conjugate base, the carboxylate anion. And the extent of this reaction is not 100%. It's less than 100%. Because it goes until equilibrium is reached, and then it doesn't go further. And how far it goes to reach equilibrium is measured by so-called equilibrium constant. Equilibrium constants, symbol K, actually called K sub A for acid, will fall in the range of 10 to the minus 1 to, say, 10 to the minus 5. Now, the equilibrium constant here, and again, I've got capital K. I don't know why I didn't put it in here, but most often it's written as K with a subscript small case a, and we say Ka. But nevertheless, it's defined mathematically as follows. When the carboxylic acid is placed in water and dissociates, reaching equilibrium, if we measure the equilibrium concentrations of the species in solution, moles per liter, and you insert those values into this expression and carry out the math, you get a single number, a constant number, which is always the same, irrespective of what the starting concentrations are. If you use different starting concentrations, the individual concentrations will be different, but if you plug them all into that formula, boom, you get just always the same value, the so-called equilibrium constant. The equilibrium constant itself is a reflection of how far the acid dissociates to reach equilibrium, something we talked about in chapter 3. I don't want to really rehash that. Now, carboxylic acids, being weak acids, they have this characteristic. If you treat a weak acid with a strong base, you generally will not get an equilibrium controlled reaction. You get a reaction that goes to completion. A typical strong base is hydroxide ions. So if I take a carboxylic acid and I treat it with hydroxide ion, this can be in the form of, say, sodium hydroxide, potassium hydroxide, doesn't really matter. Then the hydroxide base reacts with the carboxylic acid. The H here of the carboxyl group comes off as H+, donated to the oxygen, produces water, producing the carboxylate. This reaction will go to completion, not just to equilibrium. Okay. Now, one of the things also recognize here is that this product, the carboxylate ion, is the conjugate base of this carboxylic acid. A general rule, the conjugate base of a weak acid is a weak base. And if you can have the carboxylate as a component anion of a salt, we saw that previously about nomenclature, Here's an example. You could have a sodium carboxylate here. This would have the name actually sodium benzoate. And so sodium benzoate is a compound if it dissolves in water. The sodium ion is the spectator, but the carboxylate ion here, being the conjugate base of weak acid, is basic and weakly basic. It will behave as a weak base. If I were to just dissolve it in water, I don't show the equation here, it would produce hydroxide ions. It would reach equilibrium so far. But what I'm showing here is this, is that if we take our sodium carboxylate and treat it with a strong acid, there will be a favorable acid-base reaction where the HCl protonates the carboxylate anion, converting it to neutral carboxylic acid. And this reaction does go to completion. Remember the rule is if you have an acid reacting with a base, if at least one of them is strong, that will generally cause the reaction to go all the way to completion, not to just go to equilibrium. All right. So I think the important point here is that to recognize that when you see a formula of a carboxylic acid, and if it's if it's dissolved in water or solvent, or especially let's say if it's treated with a strong base, it's going to behave as an acid. If it's a strong base, it will react favorably and completely with that strong base. Flipping the coin, if you take the conjugate base of the carboxylic acid, so-called carboxylate, that carboxylate is basic, it's weakly basic, and if you treat it with a strong acid, you get a favorable acid-base reaction. The carboxylate is completely converted to the corresponding carboxylic acid. All right, the second reaction we're going to look at now. This is there's a whole lot to it, and we begin this with a specific example. If you take a carboxylic acid and treat it with one of these phosphorus or sulfur reagents, now these hopefully will look familiar. Back in the chapter on alcohol, we didn't see the PCl5, but we saw I think it was PI3 or PBr3. Those act as reagents that replace the hydroxyl group of a alcohol by a halogen. And there's really an analogous reaction here. The OH group of the carboxyl group is going to be replaced by, in this case, a chlorine. And the product then is this. This is actually a derivative of carboxylic acid. It's called an acid or acyl chloride. And we saw that before back in chapter 19. This is one of the Fieldcraft's acylating reagents. When you take this mixed with benzene, aluminum chloride, you get that acylation reaction. But this is a way to chemically make the acyl chloride. You start with a parent carboxylic acid, treating it with one of these phosphorus or sulfur reagents. The type of reaction occurring here is a substitution which the OH is replaced by nucleophilic chloride ion to produce this product. Now we're going to be more general. We're going to take this that reaction and look at it in a very general way. And this opens up the door to a very large, important type of reaction that I call acyl carbon substitution reactions. Now this will work for carboxylic acids and the so-called derivatives. In the way there's this kind of pattern way of showing things here. The L here in this general formula will be either a carboxylic acid, which would be OH, or it's a different heteroatom element. It could be sulfur, halogen, or nitrogen. All right. If we had a compound that contained the sulfur, the halogen, or let's say O carbon, you'd have not a carboxylic acid, but a so-called carboxylic acid derivative. So I'll have more to say formally about carboxylic acid derivatives later. But speaking generally here, this, as I say, carboxylic acid, or one of the derivatives, if you treat it with a nucleophile, you're going to get a nucleophilic substitution, which the L comes off and is replaced by the nucleophile. Now L, appropriately, L stands for leaving group. Now if you think about this, this is actually, you go back in your notes in chapter, I guess it was chapter 7, began our study of nucleophilic substitution reactions. There was a pattern sheet there that's very similar to this. They had a type 1, type 2. And so I want everybody to appreciate that. What we're seeing here is very analogous, very parallel with what we saw with alkyl halides reacting with nucleophiles. All right. Now, let's place this out a bit here. The leaving groups, the L, can be, as I say, either O, S, chlorine, or have a nitrogen. The nucleophile is basically going to be the same heteroatom elements, negative or neutral. For both the neutral and the negatives, you have these same heteroatom elements: oxygen, sulfur, and chlorine. Examples might be water. This would correspond to this number 2. Water would be where the H2O. The OH would be here where the nucleophile is, and then the H attached to this, and so forth. For the anion only, you can have you can have 2 additional elements here for nucleophiles: a carbon anion nucleophile or a hydride nucleophile. We're only going to see that in this type 1 case. We have a negative nucleophile. Okay. Now, that's the general pattern. What I want to show you is that you can use this pattern to predict the products of this type of substitution reaction. I'm going to call this an acyl carbon substitution because a carbonyl carbon, synonym for that is acyl carbon. And so on the acyl carbon, you have a substitution reaction occurring where this heteroatom leaving group is replaced by a nucleophile. So when we go to the next slide, we'll look at examples. Okay, before I go any further, I want to step aside and explain more what I mean when I speak of carboxylic acid derivatives. There are mainly these 4 that we're going to look at: the acid or acyl chloride, the acid anhydride, the ester, and amide. What I should probably put it in for the sake of completeness, and that's called a thiol ester, which would have a sulfur in it. And so that would be represented by this structure here. So the sulfur one tends to be slided, but it has as much merit as the others, and is a bona fide carboxylic acid derivative. All right, one thing to note about all carboxylic acid derivatives is that there is a heteroatom element attached to the carbonyl group. So the carbonyl group is here. It's got the heteroatom chlorine. Here, the oxygen of an ether group attached to the carbonyl carbon. There are 2 carbonyl carbons here, but each one has has the oxygen attached, a heteroatom group. And here the nitrogen heteroatom group is attached to the carbonyl carbon, and of course here sulfur is attached to the carbonyl group. So all carboxylic acid derivatives contain a heteroatom element bonded to a carbonyl group. They're called carboxylic acid derivatives because in principle they can all be synthesized from a carboxylic acid, as we'll explain. So at the heading would be carboxylic acid, sort of like this, COH group, and then you can chemically react that, and in fact, let me use a reaction we introduced before with one of the like PCl3. If you treat this with PCl3, the chlorine comes off and gets replaced by the heteroatom chlorine here. So the acyl chloride is derived from the parent carboxylic acid. So all of these derivatives can be prepared from, or they are derived from, a parent carboxylic acid. So that's the idea. Now, and the reaction patterns, the substitution patterns I'm going to show you, this will include carboxylic acids and any of these derivatives that are going to undergo this important substitution reaction called an acyl carbon substitution. Okay, now that pattern that I showed you on the previous slide, I've redrawn that. That's number 1, number 2. Let me go over the details there. The L group is a leaving group. It's a heteroatom group, as I mentioned. And Roman numeral 1 means that you have a -1 nucleophile. Roman numeral 2 means that it's electrically neutral, and you'll find one hydrogen covalently bonded to the nucleophilic atom. If it's identified as type 1, the idea is the leaving group comes off with its pair of electrons there, right? With its pair of electrons. And it's replaced by the nucleophile. The nucleophile comes in and attaches to that carbonyl carbon. One goes in, the other comes out. In type 2 now, the nucleophile is neutral and H covalently bonded. The leaving group breaks off and actually hooks onto that hydrogen here, and HL is the byproduct. The bare nucleophile comes over and then bonds to the carbonyl carbon there. All right, that's your pattern. All right, now let's look at some examples. I want to show you that there's a large variety of different reactions. Using the pattern, you'll be able to successfully predict the product that will form. So I hope you'll see that this is really very, very useful. Okay, so here's an example. Our task is to predict the product of this reaction. Now, we're either going to see a carboxylic acid derivative or a carboxylic acid. Here we have a carboxylic acid derivative. It's called an acyl chloride. And it's reacting with methoxide ion. So is this a type 1 or type 2? I don't have the pattern immediately here to refer to, but the nucleophile is negative, and therefore it's a type 1. So to predict the product, it says we're going to come over, the nucleophile will simply bond to the carbonyl carbon. Like this. All right. And the leaving group comes off with its pair of electrons. The byproduct then is the chloride ion broken off. That's the leaving group. And taking its place is the methoxide ion. You want to form the new bond between the oxygen and the carbonyl carbon, so we're going to draw that like so. New bond between the oxygen and the carbonyl carbon. We Don't change anything else. Don't change the connection between the oxygen and this carbon here. Leave those together. Just simply form a new bond between oxygen and the carbonyl carbon. All right, let's do another example. All right, in this example, we have a carboxylic acid reacting with an alcohol. We would need to identify, is this a type 1 or type 2? All right, so the key is to look at the other reactant here. We note that it's electrically neutral. This must be type 2. What you want to do is look for a hydrogen covalently bonded to the nucleophilic atom. We have that, the H bonded to the O. All right, that pattern, if you recall, and I don't have it drawn out here, is that the leaving group, the whole leaving group breaks off, and it's going to connect with that hydrogen here, the nucleophile, and is going to come over and bond to that carbon. So we're going to break off water as the byproduct. And then the organic product is going to attach the carbonyl, or rather the nucleophile to it. This, the O bonded to ethyl. Some people want to try to break the bond here. Don't do that. Simply look for the nucleophilic atom and make a bond between it and the carbonyl carbon. I like to draw the long curved arrow from nucleophile to its target carbonyl carbon. All right, and so this is the predicted product following the pattern. We'll note here that we're starting out with a carboxylic acid. The product is an ester. We're making a carboxylic acid derivative from an actual carboxylic acid. All right, let's look at another example. All right, now we have a carboxylic acid derivative. It's called acyl chloride, and then this is the reactant. Well, is this a type 1 or type 2? Well, you know we have an organometallic. If you recall from our previous study of organometallics, what do you do when you have an organometallic species in a reaction? Well, the first thing you do is to write it in its ionic form. And let's do that. You find the metal, look at carbon group attached to it. If there's more than one, you just break off one and make it a carbanion. So, all right, CH3 pair of dots, negative, and leave everything else and make it positive. That would be this methyl cadmium plus. All right. Now let's proceed. We've got the organometallic in its ionic form, and what's the reaction type? Well, you can see that this is a very reactive nucleophile, and it's negative. It's -1, so this would make this a type 1. And then type 1, the leaving group simply breaks off. Here is a chloride ion. The nucleophile just comes in and takes its place, bonding to the carbonyl carbon. And then if you can now go ahead and write that result. That would be this. I form attachment between the nucleophile and the carbonyl carbon. The chloride ion that breaks off now is going to bond actually to this methyl cadmium cation, and the byproduct then would be a CH3CdCl, if you follow that now, right? Okay, let's do another problem now. Okay, now let's look at what we have. Our acyl carbon species here is a carboxylic acid derivative. It's called an acid anhydride. The other reactant, to determine the reaction type, it's obviously electrically neutral. It's going to be a type 2. We've got 2 hydrogens actually covalently bonded to the nitrogen. Now the acid anhydride can be a little bit tricky. What you're going to do, look at it like this. One of the carbonyl carbons, one of the acyl carbons is the site of nucleophilic attack. So let's make it that carbon there. All right, and everything else is the heteroatom group attached. That whole piece here is in fact going to be the leaving group, and that's going to break off according to the pattern. It's going to hook up with one of the hydrogens here. So, all right, one of the hydrogens here, and the byproduct would be this. All right, and form a new bond between the nucleophile and that carbonyl carbon. All right, one hydrogen is broken off, so that product is going to be this, CH3, C double bond O, N, and then just the one hydrogen and the methyl that did not break off like that. All right, so that would be your main organic product. And then you've got the byproduct that is acetic acid there. So, all right. In this case, stand back and look at what we have. We have a carboxylic acid derivative reacting in this acyl carbon substitution to make a different carboxylic acid derivative. And if you kind of review the examples that I've done, I have a case of, let's see, a carboxylic acid converted to a derivative. You have a derivative converted to another derivative. And let's see, you can also, I haven't done it yet. Let's look at the next example. You'll see to complete that whole pattern. Let's look at the next example. All right. So we have our substrate reacting, and we have the other reactant that's going to provide the nucleophile. We've got to figure out the reaction type. I put my lone pairs on the oxygen here. All right. Well, you can see that this species here is not negative. It's electrically neutral. This would be the H and U. So, following the pattern, this whole piece is going to break off. It's going to hook up with one of the hydrogens here, making the byproduct ethyl alcohol. And then this leaves an OH. The O atom nucleophile bonds to that carbon, and your main organic product will be this. You got water, when H breaks off, hooks up with that ethyl group to make this byproduct. The remaining OH bonds as a nucleophile to that carbon, and there we have it. And now, pattern-wise, what do we have? We have a carboxylic acid derivative that's called an ester reacting with water to produce a carboxylic acid. So here we have a case of a derivative reacting to make the parent carboxylic acid. And if you think about it, you can have all those kinds of crossovers. A carboxylic acid can be converted to a derivative by this acyl carbon substitution. Can go the opposite direction. A derivative through acyl carbon substitution can produce a carboxylic acid, and one derivative through the acyl carbon substitution can produce a second derivative. Okay. Okay, I think that's enough examples, and the one other thing I want to now look at is the mechanism of this acyl carbon substitution reactions. There's two possible mechanisms that are observed. It depends on the condition. If it's base neutral conditions, the mechanism is what we call nucleophile induced. If it's acidic conditions, the mechanism is acid catalyzed. All right, let's consider the case of base/neutral conditions. The first step is attachment of the nucleophile. The nucleophile will either be anion or neutral to give this tetracovalent species here. Step 2, the L leaving group is ejected. You can see, if we watch look at the details here, there's a lone pair in the oxygen that swings in to reform the double bond as the electron pair is pushed away with the L. All right. Now, we ask, what is the rate determining step? The answer is, well, for the vast majority of substrates, that includes carboxylic acids, where this would be an OH, or the other derivatives, the slow step is number 2, the ejection of the leaving group. But there's an exception. If the leaving group is chlorine, the second step is actually fast, and the reason is that chlorine is a really terrific leaving group, and the first step is a rate determining step. So for carboxylic acids and all derivatives, esters, amides, and so forth, this second step, ejection of the leaving group, is going to be the slow step. On the other hand, for an acid chloride, when L is Cl, the rate determining step is the attachment of the nucleophile, because the loss of that leaving group as a chlorine is going to be very fast. Now, there's one more important point, though, and it's this. The vast majority of substrates, the L group leaves just as we're showing here, with a pair of electrons to make L minus. But if L is a nitrogen, an amine, then there is a difference. Nitrogen as a leaving group is terrible. It's one of the worst leaving groups, because you consider that if we have an amino group and you're breaking away breaking this bond here, you're forming a nitrogen with a negative charge. It's called an amidion, and that's very unstable and very, very poor leaving group. In fact, it's so poor it won't happen. So the point is that if L here is a nitrogen, then it can't break off by itself. It requires proton attachment, and normally that comes from the solvent. When a proton attaches to that L, then it's a much better leaving group, and it can leave. We show that at the very bottom here. So if L is an amine, that L atom is protonated by solvent before the L leaves, and here we show it. The proton is going to, the solvent rather, will be a weak acid and will donate a proton to the L group. That would be actually a nitrogen. It protonates the nitrogen group. And now it's a much better leaving group, and it can actually leave. The lone pair swings in like that. The shared pair breaks away from the carbon onto the L, producing LH as the byproduct. All right, and so that's an important difference that we're going to see. Across the board, doesn't matter where the leaving group is, chlorine, oxygen, sulfur, and so forth, the leaving group ejects by itself. When the leaving group in the L is nitrogen, it can't eject by itself, it has to have a prior attachment of a hydrogen ion to that before it can depart. All right, the second mechanism, let's examine that. This occurs under acidic conditions. It's acid catalyzed. More specifically, it's catalyzed by H+. Now you look at this whole mechanism, it looks a little bit daunting because there's so many steps. But let me try to strip it down to its simple essence. Remember, in any catalytic process, there's three phases. Phase one, the catalyst attaches to the substrate. By it being there, it makes the chemically difficult processes more easy, and in phase two, they do occur. And the last phase, two things happen. The catalyst comes off, and it's regenerated, ready to catalyze another reaction, and the product forms. Often, they occur in the same step. Not always, but often. And we're going to see that theme played out here. Step one, the H+, the catalyst, connects, bonds to the carbonyl oxygen. All right. Now, that's going to help out in this way, and that's going to facilitate detachment of the nucleophile because the positive charge in this carbon increases. That increases the concentration of this species here. Oh, by the way, that species here is an intermediate because it's four-bonded tetracovalent. We call that a tetrahedral intermediate. So this species right here, which is really an intermediate, it's called, this is its official name, a tetrahedral intermediate. Anyway, this forms, and then the next step I've called the proton shuffle step. Now, there's going to be always a hydrogen attached to the nucleophile under acid conditions. Generally, the nucleophile is not negative. Well, if it's acidic and there's protons available, they're going to be able to attach to that leaving group, and that's going to help it out. The leaving group here is, if you consider that they're heteroatom elements, unless it's chlorine, there's a challenge for them to come off. You know, they're not terrific leaving groups. The oxygen, the sulfur, and so forth, they'll come off, but they have a little trouble. But if there's acid available, the acid can attach a proton to that leaving group, and it increases its leaving group efficiency. It's a natural process. So what we need to do is to get the proton off this NU and attach to the L part here, the leaving group. That happens in step 3. It's step 3 followed by step 4. I call that the proton shuffle here. Taking a proton off the NU and attaching it to L. All right, step 5, are ready to eject the leaving group. It's got a proton attached, and so the lone pair swings in, kicks out the leaving group with its proton. All right, now we're almost there. The only one more step that has to take place, and that's the ejection of a hydrogen ion from the oxygen. In other words, we are ejecting the catalyst, regenerating the catalyst, H+, and so the H+ now reborn, as it were, is going to come back and start the catalytic process of another reaction. As well, when this H breaks off as H+, it forms then the substitution product here. All right. Now, some other detailing here. If the leaving group is chlorine, we mentioned before that that's such a terrific leaving group that each ejection is very fast. In fact, if it is chlorine, it's such a weak base, such a good leaving group, the proton won't attach to the chlorine there. That is, you see, I'm saying that in steps 4 and 5, if L is Cl, protonation of L does not occur. The Cl just breaks off by itself as Cl minus. All right. So that's one thing to bear in mind. Everything else, the carboxylic acids, the other derivatives, whether they're esters, amides, thioesters, in the acidic environment, there's going to be attachment of a hydrogen ion to the L. making it a better leaving group, enhancing its ability to leave, and it then leaves in that next to the last step. And finally, the hydrogen ion is ejected. All right. And remember, this mechanism and the other one, the rate determining step is normally the ejection of the leaving group, unless the L is, the leaving group is Cl. And in that case, the attachment of the nucleophile, that would be step 2, would be the slow step. All right, that's the story on the mechanism, and for our next class period, I have a number of videos that are posted on YouTube that take you through an animation of different mechanisms. Those are YouTube-based, and I'll post links to those so you can watch those at the next class period. Thanks so much for watching. Bye.